So this week we're going to be still talking about vortices. And as you already noticed, a lot of what we have been talking about this semester about vortices, right? And we started with lifting line theory, which is really a vertical description of the flow around the airplanes. And we are going to move around the airfoil theory, which is a vertical description of flow around the airfoils. And then we're going to be moving into viscous flows, where we are no longer describing the flow in terms of discrete vortices, like individual vortices, but continuous blurb of vorticity. So it's almost like vortices are now everywhere in the flow, in viscous flow. Basically, when you zoom into the boundary layer, right, you see vorticity everywhere. So vorticity is essentially circulation per area, right? So basically, you have a lot of, you can think about you have vortices everywhere. And it's not until we get to compressible flow where like a vertical view of the flow becomes insufficient. You need to think about something else. So today we're going to really expand our view on how vortices can describe different flow fields. Okay. So just to remind you about our starting of the discussion, we started to look at the Navier-Stokes equation, which is really Newton's second law, du dt. This is the acceleration of a fluid particle, right, is equal to, well, instead of a force over mass, we have force per volume over mass per volume. Okay, so the force per volume in our case is minus grad p, the negative of the gradient of pressure, that's the pressure force, divided by mass per volume, which is the density of the fluid, right? So that's how we started. Okay, and in the case that the density of the fluid, the rho, is uniform everywhere, we derive the Kelvin's circulation theorem. And that is, I can write it like this, d gamma dt equal to a big zero. Okay, gamma is the circulation around a line of fluid. So let's say a closed contour C, the velocity dot with dl. So essentially, if you follow that contour of fluid, right, as the contour of fluid getting advected the downstream of the fluid, the circulation around that circle of fluid, around that contour of fluid that's not fixed in space but moves with the flow, does not change in time. Okay, so that actually leads us to the conclusion that as long as that contour of fluid, which starts from very, very far upstream and should have zero circulation just by the fact that the velocity u is zero, right, in the free stream, or the velocity u is u infinity, which as soon as you move this out of the integral, if it's a constant, and you integrate over dl over closed contour, you should get zero, right? dl is a vector. If you integrate a vector from start to end along a closed contour, you get the point minus the point itself, right, which is equal to zero. Okay, so basically gamma in free stream is equal to zero, no matter what frame of reference you look at. And as gamma moves closer and closer to the airplane, it doesn't change, right, by Kelvin's circulation theorem. And it doesn't even change and stays zero as long as that contour is not cut by the airplane. Okay, if that contour is cut by the airplane, it'll change the circulation. But if the contour stays intact, never sliced apart by the airplane, the circulation remains zero. So that's how we derived that the whole flow around the airplane is dominated by a sheet of vortices that emanates right from the solid body. That sheet of vortices are basically the cut, right, where any contour advected through the airplane would be cut by that sheet. Okay, so that's what we discussed last Friday, and the consequence of that is we can use a lot of we can use this to achieve a lot of things. So basically, for example, if we know there are just two vortices in the flow, right, that then any contour integrated that's not enclosing any of these vortices would have zero circulation. Okay, and we know that a contour enclosing this vortex with a strictly circular contour would have a circulation of gamma, just by definition of the circulation. Which means if you add this contour with another contour that doesn't include it, right, the circulation is still gamma. Which means if I have now the blue contour that goes like this, that blue contour is going to have a circulation of gamma. So you can basically append to this circular contour any arbitrary additional contours that doesn't include that circulation, it doesn't include that vortex. The circulation is still going to be gamma. And the special case we looked at last week is that if I have a contour that goes from very, very far away up to very, very far away down, right? That contour can still be computed, can be kind of accumulated, so this would go like that, right, to very far away. It can be accumulated by taking that small red circle, expand it with additional contours of zero circulation, right, that doesn't go through the airplane, and all the way to this very, very large contour that extends very far up to very far down and goes around the vortex around the very far away place. That still has a circulation of gamma, right? And that gamma is basically the integral from minus infinity to infinity, the vertical component, right, of this induced velocity, right? That's something we showed that with calculus in the very beginning, but it can be shown actually without calculus, just by the fact that by Kelvin circulation theorem, basically, right? Okay. All right. So another thing we can now start to explain using the idea that any contour that does not enclose a vortex has zero circulation is the fact that why does the bound vortex have to have the same circulation as the two trailing vortices, right? Okay, so let's show it by this. So if I have a circular contour around the trailing vortex, I know. So suppose I don't know if they are the same. I suppose the trailing vortex has circulation gamma 1 and the bound vortex has circulation gamma 2. And let's show why these two circulations have to be exactly the same. Okay? So gamma 1 is a result of an integral around this contour, and gamma 2 is a result of integral around a different contour. Now imagine I break up this contour a little bit. I build another contour that goes from this point around, almost completely around this vortex, but leave a small gap. And then from the small gap, I go to the beginning of this contour. Alright? And then I go around this contour and go back to this contour. Alright? Now imagine if we trace okay, so let's imagine both around both this and this, right? We break let's see, where do we break this? We let's imagine the break of this is exactly such that the sheet of vortices coming from the trailing edge passes through this thin gap. Right? Okay. Then let's imagine, how do this blue contour, where does the fluid of the blue contour come from? Okay, so try to trace backward this blue contour fluid. We're going to find out that this blue contour fluid, this part actually, when you trace it back, comes from outside of the outside of the wingtip, right? This section, because we are thinking of this, the flow coming out of the trailing edge exactly passes through, right? So one portion of this passes, as we trace upstream, passes over the upper wing. The other passes through the lower wing, right? Okay, and this part, of course, if you trace upstream, it goes upstream. So essentially, by the construction of this contour, we can see that none of this complete blue contour is going to be sliced by the airplane, right? Is it clear, like, why that's the case? Some of you say yes, some of you are still having a kind of a blank stare. So the way I'm, because this is a 2D and I'm trying to kind of imagine 3D, so it's not exactly clear, but like the way I'm drawing these two lines that links these two contours are such that one of these lines, let's say Actually, I drew it. I think I drew it in. Let me draw it a bit more clearly so that you can actually visualize it better. So let's actually have this contour start over here and it goes outside of this vortex and ends over here, which is on the upper side of the fluid coming out of the trailing edge. And then I'm going to link it to here, to this here, which is still on the upper side of the flow coming out of the trailing edge. On the other side, I'm going to go from here, which is on the lower side of the fluid coming out of the trailing edge, go all the way to here, which is still going to be the lower side of the fluid coming out of the trailing edge. Then I follow the original contour around the bound vortex. Okay, is it clear what I'm doing? So basically, the flow coming out of the trailing edge goes straight through this little gap. Now is it easier to imagine that the whole blue contour, so this is actually closed from the outside of the trailing edge, from outside of this vortex. The whole fluid, if you trace it upstream, never would interact, never would actually contact the body of the airplane, right? Okay, which means that by the Kelvin circulation theorem, which says that the time derivative of the circulation is 0. So if the whole thing starts from upstream, having 0 circulation, as it goes over the airplane and forms a contour like that, this should still have 0 circulation. Now let's compute what the circulation is. Because the gap is very small, right? The circulation going from, let's define a direction. Let's define the direction to be this way, and this way, and then it's this way, going back, and this way, right? Okay, so this part of the circulation, let's say part number 1, is equal to gamma 1, right? Okay, the second part of the circulation goes against the gamma 2, so that part of the circulation is, so that's gamma 1 minus gamma 2, right? The third part of the circulation goes from the upper side of the gap to the upper side of the gap over here. And the fourth part of the circulation goes exactly the other way at the spatial location very close by to the upper side. So these two parts of the circulation should cancel each other. And they are going to be canceled better and better as I make the gap smaller and smaller, right? And so basically, as I make the gap smaller and smaller, the first part of the circulation approaches gamma 1, the second part of the circulation approaches minus gamma 2, and the third and fourth part cancel each other more and more precisely. So the total circulation around the blue curve should be gamma 1 minus gamma 2, right? And plus the third and fourth part, which cancels to 0. And that has to be equal to 0. That basically proves gamma 1 has to equal to gamma 2. All right? Any questions about this line of reasoning? And by the way, you can use the same line of reasoning to show why, for example, if I have multiple vortices coming out of the wing, right? And this part is gamma 1, this part is gamma 2, then of course by the same reasoning, this part has to be gamma 1, and you can also show that this inner part has to be gamma 1 plus gamma 2. Right? So you can do something very similar to show that. All right. Any questions?
So 3 and 4 are the lines, right?
Yes. Let's say 3 and 4 are the lines that kind of goes this way and back that way, right? Because the velocity should be very similar to each other if I make the gap very small. And the direction of the integration, my dl, is exactly opposite to each other, right? So that's why they should cancel each other. All right? Yes? How did I determine the sign of gamma 2? Because the original, if you follow the red contour, we are integrating this way, right? We are integrating in a way that goes from the back of the trailing edge, lower, then front of the leading edge, upper, and then back. Okay, so that's the direction of dl when I'm integrating to get a gamma 2. But when I'm getting this part, when I'm getting the blue part, I'm integrating exactly in the opposite direction. So in the integral for getting the blue number, I have exactly the same velocity field. But my dl, remember, gamma, by definition, gamma is integration over the contour, right? Velocity dot with dl as a vector. So velocity was the same no matter when I'm doing the red integral or blue integral. But dl is going to be exactly minus of each other when I'm doing the red integral versus blue integral. That's why the sign of the red integral, right, and the sign of the blue integral should be exactly the opposite. Make sense? Yeah, so basically u is the same, dl was opposite. All right, any other questions? Yeah, this is a good one. Okay, so now let's actually expand the vertical view a little bit. So we have used the vortices to describe the downwards, the flow behind an airplane and also around the airplane. So let's see what other stuff we can describe using vortices. So here's a vortex-centric view of a jet. Let's actually take a look at when a propeller creates a jet that kind of shoots air backward, right? This is a case where we can actually see the vortices. Okay, so the airplane right now is still taxiing, and we are going to see in a few seconds it starts to basically push the throttle and starts to take off, right? And usually for this kind of big airplanes, it's what they call like a constant speed propeller, which means the speed of the propeller stays the same. And as you push the throttle, what actually happens is that the pitch of the propeller change, so that the angle of attack suddenly becomes large and you're creating thrust. So right now, it's basically, it's almost a slicing air without, let's imagine almost zero angle of attack. And soon it will start to slice air at the same speed, but with a higher angle of attack. You see the vortices, right? I mean, this actually happens. We are going to explain later when we start to look at pressure, like why you can actually see vortices. So basically, right now, the thing I can tell you is that in the core, called the core of the vortices, the pressure is a lot lower. So when the air enters the core of the vortex, because the pressure is low, right, it expands, and because it expands, it cools down. So if the moisture content in the air is high, then water is going to condense into like water droplets. It's almost like cloud, right? So you can see it. Okay, so if you perform, you can look at it for a bit longer. Beautiful, huh? Okay, so you can see it anymore. It's, the background is too light. So let's actually figure out what is a vertical-centric view of a jet like that. So here we see the propeller. So let's just don't distinguish. Let's distinguish individual blades. So let's say we have, just to make it simple, let's say we have two blades, a two-bladed propeller. Okay. And what happens is that the propeller is almost like a wing, right? So as we can see that from Kelvin's circulation theorem, any air, any count of air that doesn't get sliced by the propeller should have zero circulation. So the place where the vortices come out has to be on the propeller, right? And in this case, just like a wing, the strongest, actually vortices coming out from every place on the propeller, but the strongest vortex comes from the tip of the propeller, just like a wing. Okay, so what happens is that the vortex come out of the two tips, and as the propeller is rotating, right, and the air is pushed back, remember the vortex goes with the flow, right? So the vortices essentially, so if the propeller is rotating in this direction, right, the vortices would actually go like that. So that's one vortex, and the other vortex coming out of the opposite wingtip is going to go like that. All right, that's I'm enjoying it. I mean, the actual picture is much more beautiful than this, but like that's basically how it goes. Okay, and why am I saying it explains the flow? It explains the jet, because all of these have circulation. And let's actually just take a side view, right? So let's actually take a side view of this and cut through the center. So if I cut through the center, then this is the propeller disc. And I'm going to have individual vortices that's going to pass the center slice, right? So I'm going to get individual vortices rotating that way from here. And the same vortices, when it goes around and pass here, the direction doesn't change, right? So if you look at the hand of this vortex, it's like that, right? And if you trace the same vortex through a semicircle, goes back, you're gonna see the vortices are gonna be rotating in a different direction on this plane. Is it clear? So if you just take your hand that follows. Take your right hand, so just follow one of these semicircles either that way or that way. It doesn't matter, but like as you go to the opposite direction, the flow, the rotation is going to be the opposite, right? Yes?
Isn't there some parallels here to like electricity and magnetism, like Helmholtz resonator?
Yes, there is a parallel. The mathematics of the vorticity and electromagnetism is actually almost exactly the same. The reason is that for vorticity, like vortices actually have zero divergence. So basically, remember, like the other day we were drawing a spherical or like enclosed region, right? All the vortices going in has to come out. So that's the same as a magnetic flux, right? So that's where the parallelism actually is here. Okay. Now, if you look at all these vortices and imagine that the diameter, so let's make an approximation. Yes?
Given that like the blades are rotating, like you just drew this, like it's the same scenario, right?
Yes.
If the blades are, both of them are rotating like clockwise, how come the top row is counterclockwise? Like I don't see how the flow is counterclockwise if the blades are rotating.
Yeah. The blades are rotating. So okay. So the direction of the blades and the direction of the vortices are actually not fixed with each other. So the blades are rotating clockwise or counterclockwise in an orthogonal plane, right? So basically we are looking. So let's actually draw the axis a little bit better. So let's say this is the x-axis. That's the direction of the thrust being created, right? And let's imagine this is the z-axis, and the y-axis points into the board. The blade is rotating clockwise if you see from the negative direction towards the positive x direction. But the vortices either rotate clockwise or counterclockwise as seen from the negative y direction towards the positive y direction, right? If you, for example, if you look from this side, from the positive x towards negative x, the blade would be rotating in the opposite direction. So the direction of the rotation is not actually fixed. It's depending on where you view it, right? Okay, and the direction of the vortices, as you're going to see pretty soon, depends more on the angle of attack of the blades rather than on the rotational direction. For example, like the same propeller, I can actually pitch the blades so that it actually creates a negative thrust, right? That's useful in landing if you want to stop the airplane faster. And in that scenario, you're going to see the blade is still rotating in exactly the same direction, but if you pitch the airfoils to have a negative angle of attack, the direction of these vortices are going to be completely opposite direction. Okay, the propeller would be creating, instead of creating a jet, it is going to create a wake. The propeller is going to work like a wind turbine, right? It kind of generates drag. Okay, so any other questions on like how the vortices are distributed? Now you can actually compute using these vortices if you assume each vortex has a circulation of gamma, and if you assume the spacing between these vortices are d, let's say, okay, you can actually compute how strong the jet is. Okay, how? Because imagine outside of the propeller, the velocity is u infinity, right? It's just the free stream velocity. Inside, let's say the center of the jet is at a velocity of uj. All right. So you can actually relate the circulation with how much uj is faster than u infinity. And how? By drawing a closed contour, right? So if I draw a closed contour between this and this and this and this, okay, how many vortices does this closed contour include? Well, of course, it depends on how wide this contour is, right? So let's say the contour has a width of nd. It spans n vortices. Then the circulation of that green contour should be what? Yeah, should be n times the circulation of each individual, right, vortices, right? In this case, if n is equal to 2, it encloses 2 vortices. The circulation should be 2 gamma, right? Okay, and let's equate that 2 gamma with the actual circulation we can perform, right? The integral. Okay, so the integral has 4 legs. One leg, so let's imagine this is in this direction and this direction. Okay, it has 4 legs. The first leg is nd, the length, times u infinity, right? So that's from the leg number 1. Leg number 2 goes down. So let's actually, we don't have to compute what is exactly leg number 2, because leg number 2 is going to exactly cancel with the upper leg, right? So if I choose this to be integer times the vortices, then the location it comes up in between these 2 vortices should be exactly the same as the location where the opposite leg comes up between these two vortices. Right? Make sense? So the flow field is periodic, which means the flow field here is exactly the same as flow field here. So 2 and 4 cancel each other. Okay? So we only have to compute now number 3. Number 3, I'm integrating backwards with a dl that's opposite to the velocity vector, right? So what I get is minus nd, the length, times my uj. So what I get is nd times u infinity minus uj has to equal to, well, I'm integrating this contour in the opposite direction of these vortices. So that has to be equal to minus n times gamma, right? So there I can compute uj minus u infinity is actually equal to, well, gamma over d. Okay? And uj is thus equal to u infinity plus gamma over d. So basically, this gamma over d is almost like the density of vortices, right? So if you accumulate how much vorticity, how much circulation is per unit length, that's gamma over d. Okay, so you can actually compute exactly the same integral if you trace a contour in the downward direction. Okay, so that's basically how you can figure out the relationship between the jet and the circulation. So for example, if you know how much thrust you have to create, right? If you know how much thrust the propeller has to create, you can use conservation of momentum to figure out how big uj has to be, right? Because that's basically how much. There are two things, right? One is uj determines how much air you are pushing per unit time, and the difference between uj and u infinity determines how much additional momentum, right, this jet have. So by multiplying both, you're going to get how much thrust the propeller is creating. Now what's interesting here is that you can relate the amount of thrust to this uj and then to the circulation of these vortices. So how is that useful? Well, it turns out to be useful in describing the shape of the jet. So the shape of the jet is actually pretty boring over here. It's actually pretty much straight going down, but you can already see a little bit you can already see a little bit of shrinking over here, right? Is it clear? Like the diameter of these circular vortices seems to get smaller as it passes downstream. And that's actually going to be even more significant if you look at something like a helicopter. So let's actually look at this osprey, which can transition between kind of a helicopter mode and a propeller like an airplane. It'll become even clearer in a moment. You can see these vortices being pushed down by the propeller. Okay. Now it becomes clearer, and let's pause it at some point. Oh, this is not the clearest moment. Let's actually pause at a moment where the vortices. Okay. So I think it's pretty clear from the right propeller that the vortices are not going downward. It almost goes inward, right? So the shrinking of this vertical flow as it exits from the tip is very obvious. Like in the beginning, it actually goes inward before it goes downward. So why is that the case? So this kind of phenomenon has to be explained by the vertical flows. So this is a case where I have a helicopter-like blade, right? The air is getting pushed down without much free stream, right? Unlike the propeller case where the airplane is actually going forward. So the flow field is going to be a composition of a free stream and the induced flow from the vortices. But in the helicopter case, there is no free stream, right? The free stream is, I mean, if the helicopter is hovering, the free stream is equal to 0. So all the flow, like all the velocity there is induced by the vortices. So here, imagine a scenario, I just have vortices going that way, going that way, going that way. Okay? What is going to be the induced flow at the tip of the propeller blade? Okay, so first of all, the vortices on the other side is very far away from here, right? The influence goes like 1 over distance. Actually, if you only consider small segment, it goes like 1 over distance squared, right? Remember the Biot-Savart law. So the influence are from the vortices over here. And the influence, right, if you look at the induced flow of this vortex on this point, what is the direction of the induced flow? It goes inward, exactly. So the induced flow here goes in, the induced flow here also goes in. And only when you go sufficiently downstream that the induced flow from the vortices above it and the induced flow from the vortices below it balances out, so that the flow no longer goes in. And as we said, right, the vortices go with the flow. So if the flow in the beginning goes inward, there is no way the vortices just goes downward. The vortices goes with the flow, right? So the actual flow field, the vortices are not going to stay over here. The vortices are going to go inward also. And then it goes downward like that. So it goes inward and then downward. That's exactly what we saw on the propeller, right? And actually, because it goes inward first, the induced flow at the tip doesn't even just go in; it goes up a little bit. Okay, so if you you can go to YouTube and search for wind tunnel experiments where they can visualize the vortices even better with a dark background and smoke. So the vortices actually goes up a little bit before it goes down like that. Okay, so this is how we can use vortices. We can use the flow field, use the macroscopic view of the flow field to figure out the strength of the vortices. And then use the induced flow from these vortices to explain some microscopic features of the flow field. And this is going to be very useful starting this week, because this week we are going to be looking at not so far away from the airplane, but zooming in closer to the airplane, where the shape of the airplane, the shape of the wing, shape of the airfoil starts to need to be considered. And in particular, we need to start using vortices to describe flow fields whose direction now has to follow the contour of solid geometry, right? So basically, we have to say, okay, if I make the geometry bump out or recessing like that, how would that change the flow field? And we are going to be describing all of these using vortices, right? And how does the distribution strength of the vortices affect the flow field and make the flow conform to the geometry? That's what we have to start looking at. Okay, so let's actually end this lecture by having you come up and do a similar problem, but instead of a jet, let's make it a wake. Okay, so imagine the sphere, the wake of a sphere has a diameter d. So this is very similar to the jet case, but now it's a wake. The velocity outside of the wake is u, the velocity inside of the wake, still going downstream, has a lower velocity, right? So instead of a jet where the velocity inside the jet goes faster, in a wake, the velocity goes slower, right? Okay, so can you describe the wake as a sheet of finely wound vortices with spacing small d much less than the diameter of the wake? And what is the circulation of the vortices? So I want to ask you to describe the flow exactly as we described in the jet case, right? Where it's almost like a finely wound vortices. Okay, and then try to do it similarly for a very long cylinder. Okay, so please come up. This is more of a qualitative question, but there is a little bit of a quantitative computation. Can somebody pass me the eraser here? Thank you. Yeah, I get it here.
Thank you.
Yeah. Yeah. Turn on the lights. You know, like what the wake is like, right? So you get in the wake region, the velocity is W, but outside should still be U, right?
Yeah.
Yeah, so we have flow, let's say, going towards that direction. So can you visualize what the wake looks like? So basically inside the wake, the velocity is slower, but outside is still the same as far away, right?
Yeah. I'm trying to get the intuition with this, where it's like, where we had the jet before, it was faster than free stream.
Yeah.
And we saw it twist out like this.
Yeah.
But in this case, we have a center of air that's slower than free stream.
Yeah.
Wouldn't it almost unwind in the other direction?
Yes. What you have been doing is correct. Yeah. Yeah. So it's like in the, so let's say this is the sphere, right? So let's say the flow goes in that direction, right? Where is the wake?
Probably like over here. So
Yeah, it's over here, right? Behind the sphere, right?
So you put like the vortices right here along here, right?
Yes, that's right. That's right. Yes. So you, the velocity right behind the sphere should be W, right? So it should be slower than free stream. But like outside of the wake, up and down should still be U, right? Mm-hmm. Yeah, so the way you're drawing the vortices U minus W is it's such that like the induced flow over here is going to be faster than free stream, right?
Yeah.
So this is almost the opposite of. So this is the same as the jet scenario. For a wake, the vortices needs to be rotating the other way, exactly.
For the cylinder case.
Oh, for the cylinder case, the air is in cross flow. Sorry, for the cylinder case, if you're looking at the cylinder case, I didn't say the direction, but the cylinder is across. The flow is across the cylinder, not along the cylinder. Yeah. It doesn't go through. It goes like across. Yes, goes around the cylinder.
What do you mean by?
No, so if you look at the cylinder from one of its end, the flow goes like that.
Okay. Oh, it's orthogonal.
It's orthogonal, yeah. The flow is orthogonal to the axis of the cylinder.
What does it mean, the velocity inside? Inside what?
Inside the wake.
Inside
The velocity inside means the velocity inside the wake. Yeah. Yes, that's right. Yeah. I think what the direction of the vortices has to be. Does it go that way or that way? Yeah.
We teach you questions.
Yeah.
So we have flow going in through one side and then flow coming in through the other side. So
Yes.
they're going like this. Or like there's a flow going through the cylinder,
Yeah.
W.
Yeah.
And there's flow coming over the cylinder, like U.
So the flow upstream and far away is U, right?
Yeah.
The cylinder creates a wake. Like
So
the
it's like-
wake is like it's going to be, instead of a cylindrical wake, it's almost like a flat. It's a layer, right? It's a layer of finite thickness.
Okay.
Which is going to be D.
Something approximately D.
Or
It's
maybe
not
like-
going to be exactly D. Yes.
okay.
Yeah.
But there's also a streamline that goes around like that as well.
Yes,
right?
yes.
So it's almost like putting friction on both ends of the cylinder.
Yeah.
And so as t goes to infinity, it goes to zero.
As
Right?
T
Or
goes to
it
infinity.
approaches you. So this will dissolve, right?
Oh, you mean as time goes to infinity, as you go, downstream, yes. I mean, similar as the jet, right? The jet is going to dissolve as it go very, very far away. But like, let's look at the near field.
Sure.
Right,
But it's like we're putting this like streamline of
Yeah.
U on top, but we're also putting the streamline of U on bottom. So it's like
We go like shrink it.
Yeah, so let's look at the wake. So let's say like several D downstream of the cylinder, where the wake is like the wake is no longer getting influenced by this, right?
Then it would just be like U, right?
So basically, we're looking at a place where outside of is still U, inside is W, right?
Oh, okay.
Yeah.
okay. And how does that go?
Yeah, like the main question is how do the vortices look like? I mean, because they can no longer wound like circles, right?
Right.
So this is a yeah. So that's right. So if you are saying the W goes in this direction, then this is correct. But usually in a wake, although it's slower, the velocity still goes in that direction, right? Yeah, so basically the velocity here is the summation of the free stream and the induced velocity from these vortices. Yeah, so there is a case where very close the velocity goes backwards, but like for most of the wake, the velocity still goes downstream. Yes, this is going to be correct. Yeah. Okay. Now the important, the next question is for the cylinder, right? I mean, the answer is not going to be, the numerics is not important, but like you try to imagine what the vortices look like for the cylinder case. Yes.
Like, you have to take into account this.
Yeah.
There has to be some rotational components in number 2.
There has to be some rotational component of what?
The vortices. But it's like it no longer can make a circle.
Yes.
Can it make a streamline? Like, or something that it's like, because it can't. It's not like number 1 whatsoever. It's a very different case. It's like if you had like a soccer ball being thrown through the air, and you had some free stream being blown on it, and it's like what comes afterwards. It's like turbulence.
Yeah, I mean, both wakes are like there is going to be turbulence inside, but right now we are. I mean, if you do some kind of time averaging, right, average out all the turbulence. So in this case, the vortices are just the straight lines all the way it goes from. Like if the cylinder is very long, right, then the vortices is just a parallel. Yeah.
They'll stay in the same.
Yeah. They stay in the same direction. They're just a parallel to the cylinder.
So they'll stay like that.
Yeah.
Wait, real quick. So if we have our cylinder, that drop,
Yeah.
it goes out like this.
Yeah.
The vortices are like
No,
that.
the vortices are going to be parallel to the axis
Like
of
this.
the. Yeah.
I see what you're saying.
Yeah.
Okay.
Just think about the induced flow using your right side.
Sure. Oh, wait, I get it now. Because these are all, this all makes a big collection. Yeah, yeah.
Yes.
I see it.
Yeah, just like what they are drawing here. See?
Yeah, yeah. Okay.
You get the same numerical answer, but think about which direction the vortex is wrong. Relative to the cylinder and free stream. Is it parallel to free stream, orthogonal to free stream? Is it parallel to the axis of the cylinder, orthogonal to the axis? Yeah, can you draw the vortex? Yes, parallel to the axis. Exactly. Yeah, exactly. That's the right answer. And the numerical value is exactly the same as the first question. Yeah, very good. Yeah.
Can you explain why the direction of these vortices is different than what we did
Yes.
in like the helicopter example? Because like, isn't this awake?
Oh, this is a jet. This is jet going downward. So basically, a jet means the velocity inside is higher than the velocity outside.
Okay.
For a wake, the velocity inside is lower than the velocity outside.
Yeah.
That's what I was going to say.
That was not what you were going to say. You had no fucking idea.
And a special case we're going to be discussing starting next lecture is what if the wake has zero velocity? That's the same as a solid body, right? Like it's almost like inside the wake is solid.
Yeah. So I guess then the question is like, how does the cylinder?
Oh yeah, how does the when you are drawing this?
Doesn't it still just kind of look like this at the end?
Yeah, so the difference between the cylinder is that the cylinder, the flow doesn't go in the axial direction of the cylinder; it goes across the cylinder.
Oh, so like over like the long end.
Yeah, over. So let's say if you look from one end, the cylinder looks like a circle.
Yeah.
Right, the flow goes like that. So this is like the axis of the cylinder.
Okay.
Right, then there is no way the vortices can still wound like circles, right? Because the cylinder is very, very long.
Yeah. In this example, the flow would be like coming out of the board the way we have it drawn in this way.
Yes, exactly. Yeah. If you draw the cylinder like that, then the flow comes out of the board. Yeah.
So where's some of the flow be like?
Yeah. So you're gonna have
No,
the flow is going to be parallel to the board, right? So
parallel.
So the wake is going to be like that, right? So the velocity inside the wake is W, outside is still U, right? So a wake means the velocity inside is lower. So the key question is, how do the vortices look like in this case? What direction does it run? Question? Yeah, okay.
We're confused about how to like model the sphere versus cylinder differently.
Yeah. For this is you get good numbers, right? So these are and the direction is correct, right? These are wound like that. So for cylinder it's very long, right? So the vortices can no longer wound like helices. So the question is, which direction how do the vortices look like?
That's a great question. What do you mean they're not like?
Yeah, so think about what is the shape of the wake, right? So if you have a cylinder like that, it's very long in this direction. So the wake looks like a sheet with a finite length, right? With a finite thickness. Okay, and the inside of this it's W, outside of it is U, right? Okay, so where are the vortices? So if you draw a closed contour, any contour outside of this wake, you're going to get velocity U, and if you integrate, you get zero circulation, right? If you draw any closed contour inside of the wake, you should also get zero circulation. So basically, if you draw a contour within like uniform velocity anyway, you get zero circulation, right? So that means any vortices has to be lying on the interface between outside and inside of the wake,
Okay.
right? Does that make sense?
Is it kind of end up the same as that? Like,
Because that's what we did for the sphere.
Yeah, that's correct for the sphere, except for the vortices